On the Indonesian island of Batam, the morning begins like any other. Children walk to school, shopkeepers lift metal shutters, and traffic moves slowly through narrow streets. Then, without warning, the quiet breaks. Heavy fragments of metal begin falling from the sky. Roofs are pierced. Streets are showered with debris. People run outside, looking up, unsure of what they're seeing, but certain that something is very wrong. Only a few thousand feet above them, the world's largest passenger airliner, a Qantas Airbus A380 operating as Flight 32, is in serious trouble. One of its 4 engines has suffered a catastrophic failure. Critical systems are being damaged in rapid succession. On board are 469 people, most of them unaware that their flight has just crossed a line, from routine to potentially catastrophic. This is the story of Qantas Flight 32 and the tiny defect that almost brought down the world's biggest passenger plane. November 4th, 2010. At Singapore's Changi Airport, Qantas Flight 32 prepares for departure to Sydney after a long journey from London. For Qantas, this is a flagship route, flown by the Airbus A380, the largest passenger airliner in the world. The airline is renowned for its safety record. It has not suffered a fatal jet accident since the 1,950 seconds. In the cockpit sits Captain Richard Champion de Crespigny, a former military pilot with more than 15,000 hours of flight experience. Next to him, First Officer Matt Hicks, with 11,000 hours. Behind them, Second Officer Mark Johnson, responsible for relief duties during cruise. Today, 2 additional pilots occupy the jump seats. Czech Captain Harry Wubin is assessing the captain's performance, while Senior Czech Captain David Evans oversees Harry's work. Together, the 5 pilots in the cockpit represent more than 70,000 flight hours. At 9:56 a.m., Flight 32 accelerates down runway 20C and lifts off into the humid Singapore sky. Fully loaded with fuel and passengers for the 7.5-hour journey home, the aircraft climbs steadily. It appears to be an entirely routine departure from one of the safest airports, flown by one of the most experienced crews in the world. 5 minutes after takeoff, as the aircraft climbs through around 7,000 feet, the cockpit remains calm. The autopilot is engaged, checklists are complete. Then, without warning, 2 sharp explosions are heard from the left side of the aircraft. The airframe shudders. The nose swings slightly left. The pilots recognize the signs. Something serious has occurred with one of the engines. Almost immediately, an engine indication appears on the ECAM, the Electronic Centralized Aircraft Monitoring System. It shows a turbine overheat on engine number 2, the inboard left engine. Captain de Crespigny levels the aircraft at 7,400 feet and reduces speed to stabilize the situation. He also notices that the auto throttle system is no longer available. Thrust management will now have to be manual. Following the ECAM procedure, the crew retards engine 2's thrust lever to idle and monitors the engine. While they wait, they inform air traffic control. Pan. Qantas 32, engine failure. Number 2 engine, maintaining 7,400 feet, maintaining current heading. This is an urgency call, not yet a mayday. It signals that the situation is serious, but, for the moment, under control. Moments later, a more alarming message flashes on ECAM, an engine fire indication for engine 2. Then it disappears almost instantly. To the crew, this is even more unsettling. It suggests that the sensors or wiring may have been damaged. They shut engine 2 down and attempt to discharge the onboard fire bottles. No confirmation is received. They try again, still nothing. Engine 2 is now out of service, and the damage it has caused is only beginning to reveal itself. In the cabin, passengers seated on the left side of the aircraft begin to notice abnormalities. Fuel appears to be streaming from the wing. Some will later recall seeing a brief glow suggesting a small fire inside the wing structure. Inside the cockpit, the crew's workload escalates dramatically. Engine 2 is shut down, but the ECAM continues to generate new fault messages. Fuel system warnings, hydraulic system faults, electrical anomalies, flight control degradations, spoiler and brake issues. Each message represents a procedure. Each procedure requires time, discipline, and coordination. One by one, the pilots work through the checklists, but the alerts do not stop. Eventually, the crew confronts a stark reality. Out of 22 major systems on the aircraft, 21 show some form of malfunction or degradation. This is no longer a standard engine-out scenario of the kind routinely practiced in simulators. It is a complex, evolving systems failure affecting nearly every part of the aircraft. In the cabin, anxiety rises. The cabin crew try to reach the flight deck using the emergency interphone. Under a relentless stream of ECAM alerts and decision-making, the pilots do not notice the call. On the ground, over Batam, large pieces of engine and turbine disc have already fallen onto houses and streets. By chance, no one is seriously injured. As images of the debris begin to spread, rumors emerge online that a Qantas A380 has crashed. In reality, Qantas Flight 32 is still in the air, but it is badly damaged, and its flight crew now face a series of critical decisions. The crew can only see symptoms on their instruments. The true cause of the failure will emerge later on the ground. In the Rolls-Royce Trent 900 engine that powered Engine 2, a small component called an oil feed stub pipe had been drilled slightly off-center during manufacture. That error left one side of the pipe wall thinner than specified. Over time, a microscopic fatigue crack began to grow along the weakened section. Flight after flight, under high temperature and pressure, the crack expanded. On this flight, the crack finally opened enough to allow hot oil to spray into parts of the engine where it should never be. Inside a modern jet engine, temperatures can reach extreme levels. The leaked oil ignited, triggering a fire deep within the engine. The fire weakened one of the turbine discs, spinning at very high rotational speed. When the disc finally failed, it did not simply break. It fragmented violently, sending high-energy pieces outwards. Those fragments tore through the engine casing, structural members, fuel tanks, and wiring inside the left wing. The result was a combination of damage rarely seen in service: punctured fuel tanks, compromised hydraulic lines, damaged electrical systems, and a wing that was both leaking fuel and partially on fire. For the pilots of Qantas 32, all of this destruction appeared only as vibrations, warning messages, and limited control authority. They now had to manage a heavily damaged aircraft based on incomplete and often confusing information. With the aircraft placed in a holding pattern east of Singapore, the crew faced a critical choice. They can declare a mayday and attempt an immediate landing with a heavily damaged, partially understood aircraft. Or they can remain in the air, work methodically through the failures, and accept the risks that come with burning fuel and flying in a degraded configuration. Captain de Crespigny adopts a framework made famous during the Apollo 13 mission. Rather than focusing solely on everything that has failed, he asks a different question: what still works? Together, the 5 pilots construct a shared mental model of their situation. They determine that 8 of the aircraft's 11 fuel tanks are effectively unusable. Several fuel pumps have failed, and most of the fuel jettison capability is lost. Even so, they calculate that around 2.5 hours of usable fuel remain. The green hydraulic system is gone, taking with it the leading edge slats, the outboard ailerons, some spoilers, and parts of the braking system. Road control is reduced by roughly 65%. However, the remaining hydraulic system still powers the elevators, the rudder, and inner flaps. 3 engines are still producing thrust, although some are operating in degraded modes. Before attempting a landing, the captain needs to know whether the aircraft remains controllable at low speeds, with gear and flaps extended. At altitude, he conducts a series of carefully monitored control checks, changing flap settings and observing the aircraft's response. The A380 reacts slowly but predictably. It is no longer a fully capable airliner, but it is still an airplane that can be flown. With the aircraft's basic controllability confirmed, attention turns to landing performance. Using the onboard computer, the senior check captain calculates the required landing distance for an overweight A380 in a degraded configuration. The result is sobering. In its current state, the aircraft will need almost the entire length of runway 20C, around 4,000 meters. The predicted stopping margin is approximately 130 meters, or about 400 feet. The crew requests a long final approach. Air traffic control clears other traffic away and vectors Qantas 32 onto a 20-mile final, roughly double the distance used in normal operations, giving the crew more time to configure the aircraft. They will have to land with a fuel imbalance, a damaged wing, no leading edge slats, and flaps limited to configuration 3. Approach speed will be higher than usual and the landing distance longer. Because of system failures, the normal landing gear extension cannot be fully trusted. The crew deploy the landing gear using the gravity extension system, allowing the gear to fall into place and lock under its own weight. On final approach, engines 1 and 4 are set to provide balanced thrust. Engine 3, the only engine with a functioning thrust reverser, will be used to fine-tune the speed. At 800 feet, Captain de Crespigny disconnects the autopilot and takes manual control for the landing. The descent rate is around 1,400 feet per minute, high for any landing, and close to structural limits. If he flares too gently, the aircraft may float and overrun the runway. If he lands too firmly, he risks damaging the landing gear and fuel tanks. In the final seconds, he employs an unconventional technique learned from his test flying and gliding experience, briefly pushing forward on the side stick just before touchdown to reduce vertical impact on the main gear. The Airbus A380 touches down firmly but within tolerances. Spoilers deploy partially. Only one thrust reverser is available. Maximum braking is applied. The world's largest passenger airliner decelerates hard along runway 20C and comes to a stop with roughly 150 meters remaining. For many passengers, the crisis appears to end the moment the aircraft stops. Some clap, others cry or embrace. In the cockpit, the situation remains unstable. System indications show that the left main landing gear brakes have exceeded 900 degrees Celsius and are still heating. Fuel continues to leak from the damaged left wing. Hot brakes and spilled fuel form a dangerous combination. The crew requests firefighting foam over the fuel spill and water over the landing gear to cool the brakes. Emergency services are already in position along the runway. Then a further complication emerges. Fire crews request confirmation that engine 1 has been shut down. In the cockpit, all engine master switches are in the off position. But when the captain looks out of his window, he can see that engine 1 is still running. Attempts to shut it down using alternate procedures are unsuccessful. The engine no longer appears responsive to commands from the cockpit, likely due to damaged wiring and control systems. With fuel on the ground and hot brakes nearby, a running engine presents an unacceptable risk. Firefighters are left with one remaining option: to physically drown the engine with foam and water. For more than 3 hours after landing, they continue to spray engine 1 until it finally spools down and stops. Only then is the aircraft fully secured. In the weeks that follow, Qantas grounds its entire A380 fleet, while Rolls-Royce and investigators identify and address the oil pipe defect. Operators are instructed to inspect engines for signs of leaks, and software updates add overspeed protection logic for the intermediate turbine. Qantas Flight 32 demonstrates how a single manufacturing error in a small component can cascade into a complex, high-risk event. It also shows how training, crew resource management, and disciplined decision-making can prevent tragedy, even when almost every major system on an aircraft is affected. On that day, 469 people walked off the world's largest airliner. Not because the aircraft was invincible, but because a highly trained crew managed to keep control in the face of uncertainty and severe damage. If you found this story meaningful and you want more deep dives into the real investigations behind major air disasters, don't forget to like this video, subscribe, and turn on the bell so you don't miss the next episode. And now, I'd love to hear from you. What part of this story struck you the most? The design flaw, the ignored warnings, or the human side of the tragedy? Let me know in the comments below.